introduce myself. I'm Suzanne. I work here at the Wells Reserve. Welcome. I work in our education program, and we have education, research, and stewardship that happen here at the Wells Reserve. We're one of 28 reserves in the country, part of the National Estuarine Research Reserve System. And our education program consists of public programs like this lecture. We also do school field trips, we have summer camps, we do teacher trainings, we create exhibits and interpretive signs like the one in the back of this room. So our public program calendar is on the table. It's for pretty much September through December. But there's a lot happening in the coming weeks and months. A couple of things to highlight. We have our Pumpkin Fiddle, our annual National Estuaries Day event, which is happening the last Saturday in September, a week from this Saturday. And that's a great family-friendly kind of mix between Harvest Festival and Estuaries Day. And we also have another evening lecture, which actually isn't happening here. It's happening at the UMaine School of Law, but it's part of our Beach Access series. And so it's called Whose Beach Is It? And that's going to be at the University of Maine, but wanted to highlight that one, Thursday, October 2nd. We also have a concert in the barn. We've been doing concerts all summer, and the last one is Sunday, October 12th, the DePonte String Quartet, an Owl Prowl with June Ficker and Kate, and hopefully you'll get to see a saw-whet owl that's caught in the mist nets that are put out that evening. So lots of variety, I guess is what I'm getting at. So please feel free to take one of these and also check our website, which has all the details on the calendar. Also wanted to explain those pieces of paper on your chair. This evening lecture tonight is part of our Climate Stewards evening lecture series, and it's funded by the NOAA Climate Stewards Education Project, which I'm a part of. And they like to see what people think of the programs that they help to fund. And so I've put evaluations on your chairs, and can fill those out throughout the program or at the end. And that's your ticket to be entered into a drawing where we will pick 2 names to receive our speaker's latest book. And he gave me the website where you can also get your own copy if you're not a winner, and also access it online. And that website is http://journeyintoclimate.com, which is the name of the book, Journey into Climate. So that's what those are all about. And lastly, our speaker this evening. So many accomplishments in his bio. Dr. Paul Andrew Mayewski is the director of the Climate Change Institute at the University of Maine, Orono. And he has led over 50 expeditions to some of the most remote places on Earth, and has over 350 publications, so this is just one of many, and has been on CBS 60 Minutes more than once, and also on Showtime's The Years of Living Dangerously, which was an Emmy Award winner. And I was interested to hear it's 9 shows, about 1 hour each. And the first episode is on their website. So The Years of Living Dangerously. I'm thinking maybe that would be something interesting to show at the Wells Reserve. So I'm thrilled to have Dr. Mayewski here tonight, and I'm going to turn it over to him.
in the Institute. Going to take you various parts of the world, to take you back in time towards the future. We'll talk about some of the basic science that we worked on, how we got to understand what we understand now, and then some of the applications and some of what we might have in store for us in Maine in the future. Should introduce my colleague here. I haven't seen him in 20 years, John Andrews. He's from a competing institute. I won't say what the name is. He's at the University of Colorado. So in our institute, we're one of the oldest institutes of our sort in North America, and we have a lot of different activities. We look at the modern time period. There are only records that go back 100 years or so in terms of recorded temperature. We look at satellite data. We go back in the past because the last 100 years of record doesn't actually tell you that much about how the climate system can change, how fast it can change. And then, of course, like many groups, we do monitoring and develop climate models for the future. And I'll show you a lot of this information. The last couple of years have clearly been very strange time. And they stand out in our minds. It's one of the things that actually has gotten people much more interested again in thinking about climate change and potential human involvement in this climate change. These are obviously a list of a whole series of extreme events: droughts in Australia, drought in western United States, particularly heavy rains in parts of the world. And understanding why this is likely happening and what's forcing it is obviously very important. And we will talk about some of these things. Another way of looking at these disasters is the way, for example, Munich Re. Munich Re and Swiss Re are the two big reinsurance companies in the world. They insure the insurance companies, so they're particularly interested in how much these disasters cost. And obviously there's a lot of human life involved, but just in the monetary case, the 2011 year cost $380 billion. And it's clearly risen. This is all adjusted for inflation. So whether things are worth more or whether these storms are hitting more populated areas as the population increases, they're definitely costing significantly more money. We've developed some really remarkable software in our institute that allows you to do things like look at today's weather the way the weatherman describes it, but see it over the entire hemisphere or planet, compare it to that day over many, many years, or actually work with data, find out how precipitation patterns vary in one part of the world or the other. But this is just a snapshot of one of the things you can look at it. And if you were to look at, for example, March 26th of this last year, it turns out to be pretty typical for what the winter was like. And if you looked at air temperature, you would see that this big blue area, eastern United States, and those of us who live in eastern United States know that this blue area meant it was cold. And we had a very cold winter. And of course, there was a lot of talk about that winter. However, if you look at the rest of the hemisphere, the colors are all brighter, and the rest of the hemisphere was actually warming. And if you take a look at the Arctic, in particular this portion of the Siberian Arctic, the temperatures were on the order of several degrees Fahrenheit higher than they typically are. So eastern North America was cold. The rest of the hemisphere was remarkably warm, unusually warm. Because this is a comparison between this day and all similar days going back about 34 years. Take a look at sea surface temperatures. Sea surface temperatures throughout the Atlantic, the Pacific, and certainly in the Arctic were dramatically high. In fact, just looking at that temperature, they were 7.5 degrees Fahrenheit warmer in the Arctic than they typically would have been on that day. So something very strange is happening to cause this tremendous variability in temperature. Well, part of it has to do with humans, certainly not all of it, and that's what a large part of the story is about. Trying to figure out over quite a few decades, actually, how much impact humans had, how do we interact with the natural system, which requires understanding the natural system of climate, and seeing, in fact, where we're going. So I stole this thought obviously from the web, but the arrows are my own, and big deal. This is the evolution of humans, obviously, and the first time we begin to see any impact on the climate system at all is arguably about 7,000 years ago. during extensive forest fire burning for hunting animals, and also with the release of methane from the growing of rice. It's not a big rise, but we detect it in the records that we look at. These are permanent ice core records. And then, of course, you get to the Industrial Revolution, and we begin to see a very, very big change, and I'll show you how big that change is. It's unparalleled in Earth history. Then we go to this period where there's tremendous amount of research going on, advent of computer satellites, we realize that there's something different going on, and this is what I like to think of the next stage of going into the age of climate decision, when we really have to think about how we're going to mitigate, adapt, live in a more sustainable society. And there are consequences, which I'll talk about. It'll be pretty obvious. But I think that the big punchline in my presentation is if you understand what's going to happen in the future, even within a range of possibilities of plausible scenarios, there are great opportunities. If we understood what was going to happen in an extremely volatile stock market, obviously, that's a classic example of how knowledge would provide us with good information. So I'm going to start in this early period of realization, and I'm going to take you on what I call my journey into climate. The first part of the presentation really focuses on expeditions that I've been running for the last, actually, a little bit more than 40 years. And I don't mean to imply by talking about this that I'm the only climate scientist in the world by any means. But I'll show you some of the things that I've been integrally involved in, how the science was changing around me and how we had an impact along with my teams. And in fact, it's a story of these four things. Challenges, to some degree, physical challenges. In the process of doing this, I've done 100 first ascents in the Antarctic, climbed throughout the Himalayas, crossed tremendous amounts of Antarctica, and had a great deal of adventures. But the challenges that I'm really going to focus on are the challenges of the mind. I went to college in the 60s, and in the 60s, of course, we were taught that climate was cooling. And that was the way we went about looking at things. We assumed that the climate system operated very, very slowly, and it was highly unlikely that humans could have much of an impact. Well, with time and seeing things, certain realities become clear. It's possible to make predictions, and that's where the opportunities come in. So, the research expeditions that I've been running, this happens to be a quick snapshot of the latest. It happened to be very exciting. We sailed a 72-foot boat owned by Skip Novak, a very well-known around-the-world solo sailor. We sailed from the Falkland Islands to South Georgia and back, about 2,000 nautical miles. Spent a few days on that island, which is where Shackleton ended up, looking for ice cores, which I'll be talking about, and I'll explain in more detail. But this whole process for me, and obviously for many of us, like John Andrews, started a long time ago. And my first year in graduate school, I had always wanted to go to Antarctica, and I had the opportunity to fly to Antarctica and to see this amazingly beautiful place. It was a dream come true for me. And when you go to Antarctica, as you come to the American base, which is just off to the side here, you see Mount Erebus. It's about 15,000 feet high. It's the only active volcano in Antarctica. There's a massive section of floating ice, really large. It's about 400 feet above the water there, just to give you an idea of the scale here. Each one of these icebergs is easily the size of city blocks, and this place is immense. Antarctica is 1.5 times the size of the United States. It's on average about 6,000 feet of thickness of ice if you were to spread it out evenly. And you can't be struck, I mean, you must be struck no matter when you go, no matter how often you go, by the vastness of this place. And the population obviously is basically zero. So I started working in the mountains, and the thing that became very clear, because this is what I had been taught, was that this place was timeless. Why did I find evidence of it being timeless? Well, there are large rocks that were sitting on in the mountains that poked above this 6,000 on average thickness of ice. And the best estimate, there's basically no water here, there's snow, but it dries out, is for the wind to carve this shape. It was estimated chemically it would take about 2 million years. So this rock had been sitting there in that location, basically exposed to the wind for 2 million years. That really substantiated the fact that this place is timeless. The other thing that we found, many scientists found this along the coast of Antarctica, were these young juvenile Adelie seals. And the, keep saying Adelie, small seals. And if you flip this seal over, you find the fur still completely intact on the other side. It's as if it were a live seal, but he's been abraded on the top side by the wind. And radiocarbon dating of this seal gives you ages anywhere from, depending on the seal, a few hundred to several thousand years. So in this case, this seal had died about 5,000 years ago. Yet one more reason to assume that this place must be timeless. Nothing ever changes in Antarctica. So I departed from one set of mountain ranges, made my way across the ice sheet, started to look at other mountain ranges and glaciers. And again, these snowmobiles on about 6,000 feet of ice. The mountains poke up above, and there were small glaciers coming out of the mountains. And we noticed that those glaciers seemed to have moved backwards, as if they had melted, or as if they hadn't gotten as much snow. It was the first indication, at least to me, along with taking a look at air photos and those satellites then, of how these large snow patches have changed in shape. It's the first indication that maybe this place is not quite as timeless as we thought. So as the years went on, I eventually discovered something that had been around for about 10 or 15 years. This was the methodology of collecting ice cores, drilling down in the ice sheet. And as it turns out, there is an amazingly robust record that's preserved in there. And we traversed over, and have over many years, about 25,000 kilometers worth of the ice sheet, collecting ice cores wherever we go. These are basically buried weather stations, buried time machines in many ways. In order to process these ice cores, we dig a trench in the snow. If we're able to get some light from the generator, sometimes we have one with us. You can actually take a look at the layering in the snow, and this tells you about, it allows you, just like a tree ring, to count back in time. Notice that we're wearing these clean suits. We've been out in the field for a long time, sometimes 4 months, and we're looking at chemistry in these ice cores, which I'll talk a little bit more about in a moment. Chemistry that is the concentrations are as low as 1 part per quadrillion. That's equivalent to basically 1 drop of water in an Olympic-sized swimming pool. So these are very, very low concentrations, but it makes Antarctica a great place to work because very small changes are sensitively recorded here. So I spent a few years in Antarctica. It seemed to me that this was a spectacular place. Everything we looked at and wrote about was new, but it was remote. It didn't really seem to have much to do with the rest of the world. And I had the good fortune of showing, as I was leaving Antarctica one season, showing a senator from Georgia around in a helicopter and explaining to him that this was great, great to be here. I really loved the research, but I was beginning to be concerned that we weren't doing something that was necessarily applicable to people. After all, a lot of money gets spent. And he said, well, if you keep on thinking that way in 20, 25 years, maybe we'll end up doing something that's practical. And you can judge for yourself as the presentation goes on whether or not the things we've discovered have been of value. But my initial thought was, well, I continued to work in Antarctica and still do, but I needed to go to another place too. I need to go to a place that had people, because if you work closer to people, you might find an application in your research. So I spent a lot of seasons in the Himalayas. This is one place that we went to. It's in northern Ladakh. These people are sitting on their house. It's a very, very remote community. They're only able to interact with the outside world, with any place other than this village for about 3 or 4 months a year because it's snow covered. We went into the village, and I had found a glacier in a climbing book, a book written by a woman whose name is Fanny Bullock Workman. She was a very famous climber from the early 1900s, and the glacier that she took a picture of looked as if it might be a good place to work. Nobody else had ever attempted this in the Himalayas before. So I hired a bunch of local guys. They had never done this sort of thing before. They'd actually never been up in the mountains. There was They depended on agriculture and mostly goats, but they were willing to come along, hired actually 40 of them. We were right on the Pakistani border, and from the high point that I'll take you at 20,000 feet, during the evening when it was very dark, you could actually see sparks in the direction of Pakistan, and that was the war going on between the Soviets and the Afghans. So it took us 6 weeks from the time we left the States to get up to this plateau at about 20,000 feet. It was a long trip. It was complicated to find. I just had the picture in a book. And I knew where it was roughly on the map. We had no idea what the route was, and these people certainly didn't. We went up 3 500-foot ice falls, carried all over our gear up for quite a while. It turns out that on the way up, when you get onto the rocks, which you needed to in the middle of the day when the temperatures were high, because there were avalanches coming down the sides of the ice cliffs, and the temperatures were on the order of about 110 degrees Fahrenheit, because getting high, there's very little atmosphere, you're exposed. There are clouds here, but there weren't O's clouds, and then once you cool off a little bit, you could get back onto the ice falls. And what we were looking for was basically to get up onto that flat area. And when we eventually climbed right up to that point, we found the following thing. That's the same place I just pointed to. We found these dust layers in the glacier, and these dust layers are times when there's no snow on the Tibetan Plateau, the winds blow, and the dust makes its way in. This is important. This is 1980. This is important to us because it allows us to tell year by year. And you'll see this process and the value of it becomes far more sophisticated as time goes on. The other thing, so we found a site where we could at least count in the side of the crevasse wall the number of years we drilled down, recovered core. Something very fortunate happened when we were up there for a few weeks. We had snowfall coming from both the left and from the right. They met together. And that snowfall from the left was coming from the Indo-Gangetic Plain, and from the right it was coming off the Tibetan Plateau. That's the space shuttle with a picture of the plateau. And we were on one of these small glaciers over here. Now the value of this is that the Tibetan Plateau is high and cold. The Indo-Gangetic Plain is low, fertile when you come. So warm air should be coming up here in the summer, cold air should be coming off there in the winter. And this was our first opportunity with snowfall and to actually test and see, is there a chemical signature in the snow that allows you to tell where the snow came from? The answer is yes. Chemically, we were able to tell this was warmer air. It had a lot of agricultural chemistry in it. I'll show you what that means in a minute. It also had sea salt in it. This one was colder air. It was dustier. We were lucky they came together and precipitated. And in order to prove that to ourselves, we started at 20,000 feet, went down to about 12,000 feet, and sampled all the fresh snow. And right at the dividing line between those two was the high elevation air mass, cold and dusty, and the low elevation air mass, warm and wet. So this is a more advanced cartoon version of what eventually, I won't show you the rest of it, but what eventually requires a lot of equipment, a lot of time, a lot of methodological preparation, and an awful lot of data. But this does the best job of showing you the types of things that we do. We drill in large ice sheets like the Antarctic. We drill in small glaciers like the Himalayas, the Andes. And you can take a look at, for example, sodium chloride deposited in one of these two sites, or both of these sites. And that sodium chloride ends up in the air when the wind blows across the ocean. As it does, it picks up sea spray, the little water particles get incorporated, they have sodium chloride in them, they get deposited onto the surface of the glacier, and there's a direct relationship between the wind speed and how much of the stuff you get, which is also another way of saying that you can monitor the change in pressure, because the change in pressure controls the wind speeds. So this immediately gives us a link to the source of the wind, and the source and the strength of the wind, the emissions, and where it came from, the signature. You can do the same thing for air masses coming off agricultural areas, because you can have fertilizer. This is ammonium. Chemistry is coming off dusts, chemistry is coming out of volcanoes, chemistry is coming out of industrial activity, mining activity, potentially even chemistry that's associated with changes in energy output of the sun, and also chemistries that tell you about the temperature of the air mass. If you translate all of this into what it means climatically, not chemically, we are able to basically season by season, and now we can actually literally go storm by storm with new technology we have, back decades, in some cases tens of thousands of years, with an interpretation of all of these things, temperature, precipitation, etc. And thus far, this emerging array has covered much of the Antarctic and many other parts of the planet. So once we realized that we could track air masses and emission sources, particularly things, for example, like sulfur and nitrogen, this is now in the mid-80s. Acid rain was, of course, a very big issue. And the big debate about acid rain was similar to the debate that occurred for a while about CO2. Is it really rising? Are humans really doing it? How far-flung the impacts? So I was fortunate enough to get funded by EPA to go to the top of the Greenland ice sheet, because we thought that we would be able to produce a record that would allow us to understand how far sulfur got, whether or not it was related to human activities. To do this, however, we had to drill with solar panels because we couldn't bring an engine that gave off carbon or sulfur. And what we did was to go back in time about 500 years, year by year, and this is just the sulfur plot. If you take a look, you can see that there's a lot of scatter, and then all of a sudden you get to about 1900 and the background levels go up. Well, this scatter means stuff. This particular giant spike of sulfur is related to a volcanic eruption that occurred in 1815, when there was so much sulfur put in the atmosphere that eastern North America and western Europe actually didn't have a summer. It's called the year without a summer. And it's also, people attribute the unpleasant summer to the writing of Frankenstein being written by Shelley. Because Shelley, Byron, and Keats all rented a chalet in France, and it was a very depressing summer, and so Frankenstein was born eventually. So many of these spikes, actually all of these spikes are increased levels of sulfur. Most of it related to volcanoes, particularly the big one. But the thing we were most interested in, this was proof that the sulfur was shielding incoming radiation, cooling things. This big jump in 1900 with the onset of the Industrial Revolution, this drop plateauing out in the 1930s during the Depression, rise as in World War II, continued rise, and what happens is it then begins to flatten out. And it starts to flatten out, the curve actually ends there, but it starts to flatten because we collected this in the early 80s. And up there it goes up to 80. It flattens out because that's when the Clean Air Act starts. So what we were able to show was an amazing legislative success. The Clean Air Act really did clean up the remote atmosphere. Acid rain went into the remote atmosphere, and it has radiative forcing effects if you compare it to volcanoes. And it turns out that as of about the advent of the Clean Air Act, around 1979, 1980, is when you begin to see temperatures rise in the northern hemisphere. So one could debate, I think quite substantially, that we were actually keeping greenhouse gas warming from occurring for a while by putting a lot of sulfur into the atmosphere. So it looked like a great idea to work in Greenland. Greenland's the thickest ice in the northern hemisphere. If you want to get the longest record from an ice core in the northern hemisphere, you go to Greenland. But there was not much known about it. So I started running traverses. I was advancing in my career, so I graduated from a snowmobile to a tractor. And we drove across North, Central, and South Greenland, doing snow pits and ice cores to try and find the right place. But the most important thing was to figure out how thick the ice was. And we were actually providing ground truthing for aircraft that were flying over us every now and then, and doing radar that allows them to look down through the ice. The net result is we found the right place, and in the late 1980s, with a large extra amount of money from the federal government, I was given the privilege of organizing 25 universities, or organizations in the United States. There was a companion program in Europe about 30 kilometers away, and the first season we built a camp. We spent about 24 months over 5 years in this camp, put up a 100-foot high drill. We eventually drilled down 10,000 feet right into the rock in Greenland, and we were able to count year by year, just like a giant tree, 110,000 years of record continuously. This had never been done before. And if you take a look at what the inside of the drill dome looked like, this is the inside. We were able to extract sometimes large sections of core. It took a long time because things break down. There's a lot related to doing this drilling. I'll just mention one interesting aside. You'll notice everybody who's drilling is wearing a rubber suit and they have a respirator on. The previous drillings that had been done, and we were not the first to do this sort of deep drilling. We were the first to get a continuous 110,000 year by year record. The previous fluids that had been used were unhealthy. So we found a new one called butyl acetate, and butyl acetate has another value. It's also what's used as a preservative in red wine. So we had to wear the respirators to keep from getting a little bit giddy. And so at the end of the day, you didn't need a glass of wine, you just take the respirator off. You're all set. This is inside. We dug a giant freezer this time. It took about 3 weeks to dig this out with chainsaws. It turned out to be a 100-foot-long tunnel with a bunch of side chambers to keep the ice. What we did was to produce hundreds and hundreds of very high-profile papers. And colleagues at the University of Colorado, where John is from, were involved in this. So when I was given the opportunity to direct this program, I was called into the National Science Foundation. And I'll back up a little bit so you can see the whole story. And to the Office of Public Programs by a fellow by the name of Peter Wilkins, who John knows. He's sort of a scary guy, had a lot of power. We had a lot of money. He told me that number one, this was a great opportunity for us. Number two, he would do everything he could to support us. And number three, if we messed up, that was the end of everything. We would never be able to do any kind of work anywhere again. That was the bad part of the news. The other part of the news was he said that I'm sure you'll come up with many, many exciting pieces of information. And we did. But he said you need to come up, when this is all done, you need to think about what it is that really, really sets this program apart and makes it worthwhile. And what we discovered, I shouldn't say quite discovered, it had been hinted at before, what we verified and what we characterized and what we proved was actually going to change the way climate science operated from that point on. This is what we learned. So rather than put this in pieces, I put it all together. This is from today back about 120,000 years. Forget about the bottom, but you can look at it so you see the punchline. This is what we understood about temperature from less well-resolved records. These are coming from primarily marine sediments. We understood that as about 120,000 years ago, the climate started to cool. It got to perhaps something like minus 8 degrees centigrade cooler than present. There were large masses of ice over much of the northern hemisphere. John, in fact, studies how far these masses of ice went in places like Maine and in the Arctic and other places. And then there was a massive loss of ice that occurred over several thousand years, but quite fast. This alone was an important lesson that had already been learned. And then there's a time period of about the last 10,000 years when the climate is, we thought, completely stable. So the take-home messages are ice sheets can, in a matter of 1,000 years, change their dimensions very quickly, but in general, climate operates very, very slowly. These events occur only about every 100,000 years. You can actually go back in time and see them, and basically nothing's happened in the last 10,000 years when humans have evolved. What does that mean? What it means is that you can probably, we thought, do anything you want to the atmosphere, because it's going to take thousands and thousands of years before there is a response. What we found was the following. Oops. We found that temperature, in fact, in a place like Greenland, changed dramatically during particularly times when it was very, very cold, and even when it was milder the last 10,000 years, there was still some variability in temperature on the order of 2 to 3 degrees centigrade. Temperatures in some cases could shift literally from minus 55 degrees centigrade to maybe minus 35 degrees centigrade, and they could occur in less than 1 to 2 years. Remarkable. The climate can actually operate faster than a political cycle, which is actually not saying very much nowadays. But, so these dramatic changes were not only in temperature, but they were also in storminess. Massive shifts in storms, their intensity, precipitation, temperature in less than 1 to 2 years. Once they occur, they can be sustained in the natural system for a matter of decades, if not more. This was a very, very big difference in the way one thinks. It means, therefore, that whatever triggers these things operates fast, and how do we know that we aren't going to see one of those, what eventually became called abrupt climate change events, occurring in the last 10,000 years? So, how do these things form? Well, there's an ocean component, but I'm only going to talk about the atmosphere component. The atmosphere operates much faster than the ocean. And one way of looking at these very, very fast shifts in temperature, such that whenever it gets very, very cold, it also gets very, very stormy, and vice versa, is to look at what happens to the edge of the jet stream. This is the summer position of the jet stream. Air goes from west to east across North America. In the summer condition, the edge of the jet stream, which divides cold air from warm air, is quite far north. It also is, this is not only the edge of the jet stream, it's what is also called the westerlies, and north of it, in the northern hemisphere, is the so-called polar cell, or the polar vortex, which has become a popular term in the last couple of months, but it's a term that's been around for a long time. During the winter, the edge of the polar vortex, the polar cell, the westerlies, the jet stream, whatever you want to call it, shifts significantly farther south. And these things are quick snaps in the position of the jet stream, so that instead of having the jet stream, let's say in the case of winter today, being in its winter condition quite far south for 3 months, when these snaps occur into cold periods, the jet stream has now been pushed into its winter condition for maybe 8 months, maybe 11 months. And this is the way you then, and sea ice changes go along with it. These quick snaps back and forth in atmospheric circulation were what we were seeing. So, what is it that can operate fast enough to make these abrupt climate change events occur in the natural climate system? These cartoons represent all of the major controls in the climate system. The Earth is obviously like a ping pong ball. It's gravitationally attracted to the sun and the other planets, and it changes in its position on the order of tens of thousands of years. So it does not have a red star next to it because it operates too slowly for abrupt climate change. Greenhouse gases, fast changes in, for example, methane, as it turns out, we know from records nowadays. If you can release a lot of methane into the atmosphere naturally, you can have a very abrupt shift in temperature, precipitation, atmospheric circulation, at least in parts of the globe. If you have changes in the energy output of the sun during, for example, a solar cycle, or here's an example of the edge of the sun, that's a solar flare. That little blue thing is the Earth. So obviously, we're pretty tiny compared to some of the energetic masses that can come off the sun. And but the other thing, what's wrong with this plot is that that little blue dot should actually be way over there. Nevertheless, those solar flares, these changes in energy, make their way out of the sun. And during, for example, a solar cycle, which is this 10 or 11 year variability in the energy output of the sun, you can have the ozone layer, which I'll describe in a bit more detail in a second. The ozone layer can either grow or get smaller on the order of 10 to 40% over even a 10-year period. Why is ozone important? As you go up in the atmosphere to about 25 to 35 kilometers, there ozone, oxygen, O2 plus another oxygen attached to it. That ozone is particularly effective in trapping heat above it. So without that ozone, an awful lot of the radiation would be transmitted down to the surface of the Earth, and we would be exposed to significantly more, for example, incoming UV radiation. The changes in in the energetic particles that come off the edge of that come off the sun can, as I mentioned, change that ozone concentration. It's a tiny amount of ozone. If you take all of the ozone in that layer and compress it, it would be about that thick, if not even a little bit thinner. So it doesn't take much to necessarily have a dramatic effect, and everybody's heard of the Antarctic ozone hole. That's going to play important in the story. Dusts naturally produced off deserts can shield incoming radiation. Volcanoes, I've already mentioned, the Tambora volcanic eruption of 1815. As you start to change the heating and cooling of the planet, you can actually melt ice. You can change the dimensions of ice. You can have large icebergs, which actually get pushed out into the ocean, and they can prevent heat from coming out of the ocean. They can change the color of the ocean from dark, which absorbs incoming radiation, to white, which reflects it. And as you change the melting of glaciers, particularly, for example, in Greenland, which is happening right now, you then change the amount of fresh water that goes into the ocean system. And the more fresh water in this ocean system, the more slowly it turns over. And this is one of the mechanisms by which heat is transferred around the planet. Melting of glaciers in the North Atlantic affects this turnover of heat throughout the globe, and melting of water around Antarctica actually is the biggest input. More fresh water, this thing slows down. So these are all the stars of things which potentially, it's not that they'll necessarily change something in 1 to 2 years, but maybe together they set up the right situation. Which one of these can humans impact? Without a doubt, greenhouse gases. So everything that's got a star and a circle is something that we have been able to have an impact on, and this is the classic 800,000 years of changes in CO2 that come from ice core records, not our records, but colleagues in the US and in Europe and in Australia. And if you take a look at the levels of ozone over the last 800,000 years, you can see that they're within a fairly well-defined range. And then all of a sudden, as we come into the last few decades, there's this dramatic rise. We're well above the 400, pushing our way to who knows what. What's important is the magnitude of the rise. What is, in many ways, almost more important is the fact that the rise is 100 times faster than anything back in the last 800,000 years, and arguably anything back going millions and millions of years. Now all of a sudden you've got this massive impulse of CO2 changing, and methane, changing the heat balance of the planet, and you have the kind of imbalance needed potentially for an abrupt climate change event. What else can humans do? Humans can certainly affect the amounts of dust in the atmosphere, from forest fire burning to deforestation to urbanization, all sorts of things. Humans can also, through, for example, greenhouse gas warming, can melt the edges of glaciers. I'd be happy to answer questions about how this actually works along the coast of Antarctica. It can melt glaciers in Antarctica and Greenland, leading to influxes of fresh water, which slow down the heat transport around the planet. Another way in which humans could affect abrupt climate change. And then the reason I talked about solar variability and its effect on ozone is that we've created, as a consequence of the emission of chlorofluorocarbons in the northern hemisphere, it turns out that chlorine and fluorine are extremely effective in destroying ozone. And we have an ozone hole in Antarctica in the roughly the August to October time frame that, based on research that we've done, is probably it does occur naturally, but in the last 20 to 30 years, it has been larger than it certainly has been in the last 10,000 years, as far back as we can go. So we can fiddle around with ozone, which is part of the natural process, and all of these other things. And the bottom line is that what we've done is to basically take the natural forcing and put it on speed. So, the last 10,000 years, however, are not the time when we have the most dramatic of these abrupt climate change events. Turns out it's, I should say prior to 10,000 years ago. In the last 10,000 years ago, 10,000 to the present, these events have been much more subdued. They've been in a place like Greenland on the order of arguably 1 degree centigrade, maybe 2 degrees centigrade, and they have not necessarily been globally distributed all at exactly the same time. But there are some pretty amazing coincidences that occur that are more than coincidences. This particular plot comes from the record of Greenland. It's related to these quick shifts in atmospheric circulation. And this particular record tells us about times when there was not so much sea ice in the North Atlantic, which would be more summer-like conditions, times when there was a lot of sea ice in the North Atlantic. And if we look at the first, most dramatic decrease in the extent of sea ice in the North Atlantic, it's about 4,200 years ago. 4,200 years ago is spot on, and there are plenty of papers now, with the collapse of the Mesopotamian Empire, which, as it turns out, covers modern-day Syria and parts of Iraq. And this drought occurred all the way from the Middle East right into eastern China. It led to the complete collapse of civilizations because by then humans had started to build up civilizations. You're going to stay in one place, you obviously need water to supply. And what happened is the shift in circulation going to more summer-like conditions took all of the moisture-bearing air masses that would have normally come into ancient Mesopotamia, shifted them a few miles or tens of miles farther away, therefore no more water, and you can't dig irrigation ditches fast enough to get water into a large city. They just simply left. Same thing happened to the Mayan civilization in Central America around 1,100 years ago, and then around 1,000 years ago, also during a very mild period, Greenland was colonized. And in fact, at that time, it was probably greener than it is now. Cathedrals were built, and from about 1,000 years ago to 600 years ago, a period of about 400 years, this area was occupied, and the people, the Norse who lived there, had a completely European lifestyle. They never really took on any of the cultural traits of the local Inuit. They required yearly resupplies from Europe for their cotton clothing. They did have sheep for wool. They grew crops that would grow in warmer climates. And suddenly, 400 years ago, 600 years ago, AD 1400, this is very fast. In about 10 years, Greenland gets largely surrounded by sea ice, particularly from the south, where these ships could come from Europe, and they're cut off and people starve to death. We know they starve to death, archaeologists know, because you can begin to see them stop. They're no longer sheep and cows to eat. They start eating dogs. And then the insects that start to come into the house are indicative of very, very meager amounts of food. So here are two dramatic examples of how quick abrupt climate changes, they don't have to be global, but on a regional scale have a dramatic impact on civilizations. Two in the case of drought, one in the case of cooling and sea ice. So the ice cores were looking pretty encouraging to us, and we decided that we would begin to look more carefully at how humans might have impacted the chemistry of the atmosphere. So we were still going to Antarctica, and we decided that we would try to find the cleanest snow on the planet. And why would you want to find the cleanest snow on the planet? You would want to find it, you would go to the middle of Antarctica because it's as remote from human activity as you can get. You want to find the cleanest snow on the planet because that gives you a baseline for what the natural atmosphere would be like. And as you go more and more into industrialized areas, you have a better idea of how much things could change. If we found really clean snow here, then we would start to drill down in various parts of the world to see how humans might have impacted the chemistry of the atmosphere. In order to collect this clean snow, what you do is you get in a snowmobile, you drive into the wind for about a week, and then you get off on your skis, and you ski for a few hours, and then you dump the skis, and you walk for a while into the wind all the time, and then you put on clean clothes and you sample snow that you hope has, we know the air masses that we certainly weren't polluting them ourselves. Well, the long and the short of all of the findings, looking at this clean snow, realizing that even that snow was not that clean, and then drilling ice cores all over the world, comes up with what I call these undeniable human impacts. The time scale on here goes from roughly today back 5,000 years. And it actually could go back, in some cases, 100,000 years, and I'd make the case that some of the things we're talking about are unparalleled in Earth history. But the focus here is what's happened in the last 150 years, and if I made this scale longer, you'd never see what happened in the last 150 years. Well, as population increases, obviously greenhouse gases increase, we get chlorofluorocarbons, humanly engineered chemicals, obviously never occurred before. Increased levels of radioactivity from above ground bomb testing. We were the first to find Chernobyl in the southern hemisphere, that's South Pole. Levels of acid rain increased, I already described that. Increased levels of things like copper and lead. In fact, even 2,000 years ago, there were slight increases in copper and lead from metal smelting. This is a log scale, so this looks a little higher than it should. And increased levels of mercury. All of these things have dramatically changed in the last 150 years. I would make the case that there has never been a time in Earth history when the chemistry of the atmosphere looks the way it does today. And when you take into account the fact that we have ozone holes that allow ultraviolet radiation in, and we have these chemistries in the atmosphere, we really wonder how long we will continue to actually look and physiologically be the way we are today. So, another catchy, depressing phrase, we call this thing the toxic climate cocktail, because that's really what we created for ourselves. And we focus on air because you can drink clean water. If you go out and buy clean water, you can purify it. You can buy good food, but you cannot get away from the air where you live. We developed software in our institute so you can actually see how good the air quality is in the place that you live. It's called 10 Green. Go to our website and see you can see all of the data and numbers that allow you to tell how dirty or clean your atmosphere is. So it's a toxic climate cocktail because, of course, as warming occurs, you have diseases migrating. In the case of Maine, I moved to Maine in 2000 with no Lyme ticks. Now there are tons along the coast. Obviously, things like drought, which I'll talk more about. It turns out that in the United States, we have unhealthy levels of very small particulates in the atmosphere. These are the ones that get inside, that go through the filter system in your lungs. We have unusually high, I'm not going to say they're dramatically high, but they're unhealthily high levels of some toxic substances, in particular cadmium, as you get close to industrial emission sources. And cadmium in the air is one of the contributors to autism in small children. And then, of course, and this is demonstrated by the Heinz Foundation, the Heinz endowments that we work with. And then, of course, ocean acidification and everything else that goes on. I'm not focusing on the ocean at all, but the ocean, what's happening in the ocean is very, very critical because of the food supply. So Antarctica clearly looked like a great place to work. I decided that the next thing to do was to get a whole bunch of ice cores from Antarctica. It's a giant place. It was going to give us all sorts of understanding about things that that if you didn't start monitoring them a long time ago, the only way you could find them is in ice, for example, changes in chemistry. So in 1989, I put together a program called ITAS, International Trans-Antarctic Scientific Expedition. My wife is an artist. We were sitting in France before I went to a meeting where I presented this, and I asked her to do a little sketch. Whoops, she hates me to say that because it's pretty primitive. But I like it because, my wife did it, but I also like it because that's what the real thing ended up looking like, oddly enough. And now I've got 21 countries involved in this program. We've traversed thousands and thousands of kilometers around Antarctica. I've led the U.S. programs, which have been this part of it. And the program still continues. It's a big international success. What did we find out from this series of ice cores all over Antarctica, plus a lot of work done by many colleagues working in the ocean, ecosystems, etc.? What we found out is that the so-called sleeping giants, the large ice sheets, Greenland and the largest one, Antarctica, are really beginning to change very, very fast. Much faster, not in the interior necessarily, but certainly around the edges, much faster than we ever thought back in the late 60s and the 70s, and for that matter, even the 80s. And this is a big deal because as the edges of the ice sheets begin to change, you go, in the case of Antarctica, portions of South America, portions of Australia, portions of Southern Africa begin to get affected. So we've extended our work into many other parts of the world. This is a small fishing boat that we use to get to one of our sites in Tierra del Fuego. We ended up working on the most southern ice cap, high ice cap in the world, where you have you're completely exposed to this was a very bad idea to go up here. completely exposed to the Pacific Ocean, the Atlantic Ocean, and the Southern Ocean. Got up there on a fine day, and then spent the next 17 days pinned down in tents with 100-knot winds. And it didn't turn out to be a very good place scientifically. So, but it was worth it, and what we've done is we've made our way north a little bit to places where the record will be better preserved. Worked since 1979, worked in a lot of parts of the Himalayas, including Tibet Himalayas, and this we've spent 5 seasons on Everest at close to 24,000 feet there. Most recently, in the last few years, we've started to work in the Andes. The glaciers are disappearing like crazy in the Andes. This is not only a problem for us because we want to get the records, it's a more significant problem for large population centers. This particular site, which is called Pongatito, that we've visited several times, and we've drilled an ice core down through Pongatito, is about 100 kilometers from Santiago. Santiago is the largest growing city in Chile. It's 4 million people, and this glacial water is critical as a water resource and also as their hydroelectric power. But the glaciers are getting smaller, so we're trying to get records together, drill into these glaciers to see why, and what is it exactly? Is it getting less precipitation? Is it melting? Are the winds shifting that bring the precipitation, which turns out to be the answer? And are humans putting, because of copper smelting and local surface mining, are they having enough of an effect on these glaciers that they're melting even faster? So, that particular expedition, we were fortunate enough to have a film crew for the Years Living Dangerously. The main producer in this is James Cameron, who did Avatar, and if you get a chance, you could go to the website. You can see the first in the 9-part series. We're in the 9th part. It has famous hosts like Harrison Ford and Don Cheadle. It's an amazing series because it's not just about the science, it's about how people are impacted, etc. And we just, as a film, we just got married. So, why do we care about the atmosphere? This is an animation of the atmosphere going back day by day for a particular year. These are the westerlies, these brighter things. There's the westerly in the northern hemisphere. You can see the flow lines for the air masses. You can see that these air masses shift up and down, and as they do, they transport heat, moisture, and pollutants. And I'm going to focus mostly on the moisture. If we didn't have greenhouse gas warming, this would still be the way for the mid to low latitudes that most of the heat, moisture, and pollutants will be transferred. And the big question is, have these moisture sources shifted so that we're opening up more drought areas in places that people live, and why have they shifted? So, the answer is they have shifted. I'll show you how much they've shifted, and the reason that they've shifted is because of uneven heating of the surface of the Earth. Greenhouse gases CO2 has risen 100 times faster than it ever has before for all purposes, but it has yet to still evenly heat the entire planet, and it'll be a while. What it has done is dramatically unevenly heated the planet, and it's the Arctic that has heated the most. This shows you this is from our software. You can generate this figure yourself. Last 10 years compared to the previous 20 years, when the climate records, when the recorded records are most trusted, shows us that there are times that throughout much of the Arctic in the last 10 years, there's been on average a warming of close to a couple of degrees centigrade. You go to the mid-latitudes, there's a little bit less warming, and let me just see if I have this up. I'll talk about the southern hemisphere in a second here. But let's focus on the Arctic, right up here, and see how much warming there's actually been up there. It's been a dramatic warming. In the last 5 years, this portion of the Arctic has warmed by 8 degrees Fahrenheit. And you take a look at the abrupt climate changes that we were studying in these glaciers, the last time you get a warming that is that fast and that much is potentially 12,000 years ago. The difference is, and this is the beginning of the climate period that we live in now, that civilization has occurred. The difference is that at that time it was over a much, much larger area. But we are seeing a change potentially that is unparalleled for that part of the Arctic in the last 12,000 years. And it's super important because in the process, it is completely changing the atmospheric circulation patterns in the northern hemisphere. I'll show you how. If you look at the difference in what are called melting days, how many days during the year you get low. So this is effectively how long summer is. You find out that this part of the Arctic has actually doubled in the length of the summer. This is dramatic in 5 years. A place like Maine, in the last 5 to 10 years, we've gone one growing season south. Obviously much less dramatic, but nevertheless still impacted. And as many of you know, scientists at the University of Maine recently demonstrated that parts of the Gulf of Maine are arguably warming faster than certainly any other water body in the Northern Hemisphere, if not over the whole planet. So this situation in the Arctic, with this massive, fast warming, potentially unparalleled in the last 12,000 years, has other consequences. This is a paper that just came out from a team at the University of Alaska in Fairbanks, Shakova, and she demonstrated that as this warming occurs in the Arctic, there's permafrost, frozen ground. That frozen ground has a lot of stuff in it. Amongst the things it has in it is methane. Methane is 30 to 60 times better at trapping heat than CO2. And this methane, it's been known for a long time that there's methane popping up out of the permafrost. You can see lakes in Alaska with these bubbles popping out of them. That's the methane coming out. And what this team was able to demonstrate is that there is the rate of methane release, at least for this part of the Arctic, where the ocean is warming, is at least 2 times more than was projected. So all of a sudden, something that's 30 times better at trapping heat is operating twice as fast as we thought, at least for this area. And I heard an NPR discussion by Shakova, and she said that the paper may say 2 times, but they really think it's closer to 4 or 5 times. They just assumed that nobody would ever believe it, so they didn't actually write it. They were overly conservative. This is big because methane, along with this fast rise in greenhouse gases, you can expect fast responses of rock climate changes from this. So now let's look at the southern hemisphere, where the warming has been quite different. Parts of the southern hemisphere, actually the ocean is cool, which is pretty amazing. The Southern Ocean is the largest ocean on the planet. It can absorb the greatest amount of heat, and it's actually cooling. I'll tell you why it's cooling. There are parts of coastal Antarctica that are dramatically warming, but arguably interior portions of Antarctica that are cooling by a small amount. So, completely different than the Arctic. This has to do with the presence of the Antarctic ice sheet at the pole, the fact that it's surrounded by ocean, and I'll show you what this translates into in atmospheric circulation. The atmosphere is important because wind transports moisture, temperature, heat, and pollutants. So let's look at the let's look at the northern hemisphere first, the side view of the northern hemisphere. We know that the Arctic has been warming dramatically. We know that the mid to low latitudes in the northern hemisphere have been warming, and this is the jet stream. It's a slice out of the atmosphere. The jet stream goes very high up into the atmosphere. That's where it's actually fastest. That's where you want to get an aircraft in so that you can save fuel. But the important thing to us is that we have warmer compared to warmer, and that means when you look at the temperature profile from the Arctic to the mid-latitudes, the temperature difference is not steep, it's very, very little temperature difference. The smaller the temperature difference, the weaker the winds. These winds run basically almost along latitudinal lines, and the less the gradient, the weaker the winds. I'll expand on this in a second. If you go to the southern hemisphere, again, there's a certain amount of warming in parts of the southern hemisphere, but the big deal here is the presence of the Antarctic ozone hole, because the ozone is being destroyed during part of the year over Antarctica. The heat over the surface of it, so it's strange to think about heat over the top of Antarctica, but there is heat over the top of Antarctica, is lost. The net result is that the atmosphere over this very high ice mass has actually gotten a little bit colder. That's gotten warmer, so the net result is you actually steepen the gradient with this one. From the South Pole to the mid-latitudes, the gradient has steepened, cold to warm, and the winds that separate these two things speed up. If we look at a map view of this, there's the same plot on the top, and go to the southern hemisphere, these are the westerly winds, this ring, and when you get steepening of the gradient, the winds strengthen. And they create a barrier. They actually prevent cold air from the Antarctic from going north and they prevent warm air from equatorial regions from going south. It's like if you speed up the wind and there's less transfer of heat across it. This is very, very important because this basically leaves Antarctica isolated. And when the Antarctic ozone hole eventually heals, these winds will weaken and warm air masses can make their way into Antarctica more quickly. In addition, because these winds are speeding up around Antarctica, they're taking surface ocean currents, dragging them, exposing cold water from the bottom, and that cold water can absorb more and more CO2. Recent studies in the Southern Ocean indicate that the warming of the Southern Ocean is not just at the surface, the warming is flowing all the way down, in some places, to the bottom of the ocean, several thousand meters down. That's big. That means that the Southern Ocean is buffering things for us, but it can only buffer so long. In the process of buffering, it actually acidifies the ocean. And then once this wind barrier breaks down, a lot of heat's going to be released, and that heat will be available to go into Antarctica. The opposite's happening in the Arctic, where we have warm against warm. The westerly winds moving in this direction have actually weakened. That means that warm air masses can penetrate farther north. Cold air masses can penetrate farther south. The barrier that would normally be strong is now weak. This is work done by two colleagues at Rutgers. It's really it's a very important contribution. I put these arrows on here. For the northern hemisphere, the westerlies get weaker. As I mentioned, this north-south transmission of air, cold air coming down, warm air going up, strengthens. You get more exchange. The barrier is weakened. What they've shown is that for a typical pattern of the edge of the jet stream, also called a Rossby wave, this edge of the jet stream, under these circumstances becomes more and more embayed. Cold air goes farther and farther south. Remember, Florida had a particularly cold, unusually cold winter. Well, when you do this, the more you expose cold air to warm air, the more instability you have in the climate system. And that's exactly what, in the northern hemisphere, what we're going to have more instability whenever cold and warm air comes together. The other thing that they discovered was that the longer these tongues of cold air, the slower they travel, which is one of the reasons why when the cold sets in when it set in Eastern North America last year, it was very slow moving, so we had many, many more days in a row of cold temperatures, and potentially will this next year. So, the atmosphere is critically important. It transports moisture, transports heat, and if we look at the projections for 2070 to 2100 using the Intergovernmental Panel on Climate Change, a remarkable document that basically puts a ton of information together. It's in some places potentially a bit conservative, but it is a great framework. They project drying, I'm focusing particularly on Central America and the Middle East, exactly the places we showed over the last few thousand years that when the climate warms, you get drying. This is really, really important because these places that are drying are areas that are very, very critical, obviously, from a variety of social and political reasons. So in addition to the drying in South America, brown means dry, and in the Middle East, there's been drying in other parts of the world. And this doesn't look as dramatic because, again, I'm going back to the existing record. This is the last 15 years compared to roughly the previous 15 years. You can see obviously drying in the Western United States, some drying in the Middle East, a little bit of and significant drying in parts of Africa. That little bit of drying alone in the Middle East is, if you look at Years of Living Dangerously, Tom Friedman, who's a very well-known writer who writes a lot about climate change, he interviews people in Syria, and they claim, and these are farmers, and they say that one of the reasons that there has been so much political unrest and potentially contributing to the Arab Spring is the fact that they can't grow crops. You go to Somalia, where, of course, the farmers can no longer grow crops, and they turn to other things, like piracy, in order to get funded, to get their money. Places like Australia, southern Australia, the westerly winds that normally bring moisture have moved farther south. As long as these winds stay more southerly than usual, the tip of Australia will continue to stay on drought. There are places, however, where the winds are, because of the fact that the winds are intensifying, you actually get an increase in precipitation on the western slopes, on the windward slopes of southern South America, and not so obvious, but also southern New Zealand because you're getting more moisture being transported. And in the process, as I just mentioned, you also get transport of surface ocean currents and upwelling of cold water and incorporation of CO2 and heat. One place that I find particularly interesting because people don't necessarily talk about it a lot is Mali. I've been working with several African countries lately, talking with them about climate change. And this is the country of Mali. It's a landlocked country. You take a look at how much precipitation it got from 1979 to 2002. You see in the lower two-thirds, in the upper two-thirds, of Mali, it got nothing. It's dry. In the lower, roughly one-third of Mali, it arguably got something close to a meter. If you take a look at the last 10 years compared to that, you take a look at southern Mali, they've lost a half a meter of the meter that they did have. So Mali basically is almost entirely dry now, and they're completely landlocked. And nobody surrounding Mali necessarily wants the people from Mali coming into their country. If you look at reports, for example, this particular one was done for the National Security Agency by a military advisory board, and this is a prediction for what will happen forgetting about climate change, just based on population increase over the next few decades. And clearly, they estimate a 35% increase in demand for food, a 50% increase in demand for energy, 40% increase in demand for water based on population increase alone. If the change in the winds transporting moisture continues in the direction the trend is going, these estimates will be extremely low for the impacts on food, water, and energy. So the other side of the coin is, where will there be a lot of water in the midst of these dry areas? I mentioned that we've been working with several African countries. One of them is Lesotho, and Lesotho is right in the middle of South Africa. It is landlocked, and in Southern Africa, the expectation is, based on the models, it'll be very dry, except for Lesotho. It's a tiny country which actually has the highest incidence of AIDS in Africa, but also has tons of water. It's a high country, and therefore it captures a lot of water, but it's a small landlocked country with basically all the water of the surrounding area. We're also working in Tajikistan, and in Tajikistan are the Pamir Mountains and the Pamir Glaciers. These are the largest masses of ice outside of Antarctica and Greenland, and Tajikistan has immense water resources, just like Chile. They get their drinking water and their hydroelectric water from the Pamir Mountains. However, they are landlocked, and they're surrounded by Afghanistan, Iran, Uzbekistan, Kyrgyzstan, China, all dry places. So you ask yourself, if you were a powerful country with no water, and there was a country right next door to you with these sorts of places, how would you get your water? I highly suggest that if you are interested in these sort of things, you go to this, it's a website, Center for Climate and Security, and this happens to be an article that came out not long ago in which they report the first exchange of fire, minimal but nevertheless, exchange of fire related to this water dispute between Tajikistan that has water and Kyrgyzstan that doesn't have water. So, you begin to boil these things down. The issues in question for the future are health, from warming to chemistry, water availability, extreme events, storms. And I haven't talked about sea level. I'll mention that very, very briefly, because I have a slightly different take on it than what you might have heard so far. And the question is, how will these things change in the future? Will the changes be linear? That's pretty much the way the models predict it, because the models are only working with the last 30 to 40 years of data. And except for this big change in the Arctic, everything is linear, and the models can only run off existing high-resolution data. Or will there be an abrupt climate change? Expectation is yes. I would say there's already been one in parts of the Arctic. Or will there be a series of abrupt climate changes? And it's really critical for, we're developing a conference, we have a conference in late October at the University of Maine for Maine communities, which are becoming very interested in how they're going to adapt and potentially have more sustainable societies. We're going to developed this idea of plausible scenarios, not just thinking within the linear box, but the abrupt box and others. Plausible scenario planning is not what's used, has been used thus far by IPCC, but it is what's used by the military, it's used by big corporations. And plausible scenario planning is where you think about what could happen in the next 20 to 30 years. Could there be a 3-degree centigrade change in central Maine in the next 20 years? And you just go through and you see what would be affected versus a linear change, in which in the next 30 years might only be a 1-degree centigrade change. So, quick summary of sea level. Sea level estimates for 2100 have gone all over the map. The latest IPCC 2013 has estimates by 2100 as low as 26 centimeters and as high as 98 centimeters. I was one of the people who put together a report about the Antarctic, and we begrudgingly said it could be up to 140 centimeters, begrudgingly because some of us thought that was too high, some of us thought it was too low. So we have this range from 26 to 140 centimeters, big difference. We go back to the geologic record. It turns out that the last time the temperature was 2 degrees centigrade higher than today, which is a conservative estimate for temperature rise by 2100, sea level was 4 to 6 meters higher, 12 to 18 feet higher than it is today. If you want to see the last time the temperature was 3 degrees centigrade globally, you have to go back 30 million years, and 3 degrees centigrade is still within the range, the moderate range of expectation for 2100, and at that time sea level was 60 to 90 feet higher. So there's a lot more sea level out there, and I would say that thinking about 2100 doesn't really make a lot of sense, because if you begin to build seawalls, move residences, you don't want to move them. First, it could take 20, 30 years to move them, and then you've only got 50 years left before the sea level exceeds them. So you need to think beyond 2100, because inevitably these rises will occur. The question is, how fast will they occur? This is something, the next one will be. This shows you all the 15 of the 20th largest cities on the planet are in coastal areas. I think 75% of the world's population live in coastal areas, so this is a big deal. And this is what I was about to say. John's very familiar with this work. The question is, how fast has sea level risen in the past? There is a time period when the glaciers were melting, and as a consequence, when glaciers were melting, and as a consequence, sea level was rising, when there was melt of Greenland and arguably melt a very large portion of Antarctica, and there was actually, within 500 years, a 20-meter sea level rise. If you take that 100 years, that's 13 feet in 100 years. And right now, the biggest estimate from IPCC is 3 feet in about 100 years. So I would say that, fine, we need to consider the fact that the sea level rise might not be great, but there's an awful lot of evidence out there that suggests that it could be much faster than we thought and much bigger than we thought. So I would contend that climate change is certainly not, it's considered to be a political issue. It's not a political issue. And in fact, it goes well beyond science. It's a security issue. And it pervades everything that we do. Our health, I don't need to explain how it impacts our economy, the number of extreme events, catastrophes, and obviously between the melting of the Arctic Ocean, climate refugees, water towers, etc., geopolitically, very, very big implications for the future. The Pentagon realizes this. Many large companies realize that it's important for communities to start thinking about it. So, all of this depressing stuff, what's going to happen in the future? I still contend that if you understand what's going to happen in the future, or even a range of expectation, there are opportunities. And we'll take a look at what the opportunities are for Maine. It turns out that Maine doesn't generate most of its pollution. Most of its pollution in the form of ozone comes up along the East Coast. Acadia National Park is the third most polluted national park in the country, unfortunately, although it's beautiful and clean most of the time. We get the rest of our air from the west and from the north. So if we can convince these other places through legislation to decrease their emissions of particles, cadmium, we will have much cleaner air, and then the process will reduce greenhouse gases. This is something that's critical. It's important for us to obviously be healthier. We have the right to be healthier. We have, and the costs for our healthcare would go down dramatically. Plus, of course, we would have better quality lives. Wind power, in terms of Maine. We are in a phenomenally strong situation in Maine with there's wind power on land. I'm focusing mostly on the wind power offshore. Our university has been very, very much involved with Dogger and others in developing the props for these offshore systems. It's not cheap, but when you compare the cost of renewable energy of this sort with rebuilding our energy infrastructure, which is actually getting quite old, it's not as expensive, and the long-term benefits are remarkable. Better jobs, energy independence. Maine could potentially produce, based on the planned array of offshore wind, which has some environmental problems, but minimal compared to a lot of other things. And if you throw a little bit of money at the science, you might be able to figure out some fixes for that. But we have a potential of between 10 and 30 nuclear power plants worth of energy offshore from Maine. This is probably one of the most important things that Maine could do for its future. These are not only better jobs, but they're really high-quality jobs too, servicing these things. Maine, if you take a look at the distribution of high winds around the planet, the Gulf of Maine is definitely one of the highest winds, both in the summer and in the winter. The other thing, which is bad, but it actually may turn out to be good for Maine, is the opening up of the Arctic. This shows the various routes that explorers have tried to take to get through the Arctic. Well, you can now sail through the Arctic in the summer. Large Russian vessels are moving back and forth, moving immense amounts of equipment. It's a much shorter trip than going through around the Horn, which people used to do through the Panama Canal. And there's a company that has now moved all of its offices from the east coast of the United States, an Icelandic shipping company, and they now have moved to Portland. And they believe that Portland will be the first call of entry for vessels coming through the Arctic and also transport back and forth to Iceland, their home country, and Europe. So it would put Portland and portions of the seacoast area back to where they were as major shipping centers. This requires care, obviously. We want to do it in the right way, but if we're smart and know what happened that was wrong in the past, it's possible to do it in the right way. What do you do with all this energy? What happens if nobody wants to buy our energy? Well, you begin to create the largest set of greenhouses on the planet. If you want the best vegetables in the world, go to Iceland. They're greenhouses, they're the freshest vegetables, they taste delicious. So we could, if nobody wanted our energy, we could certainly do this. And organic foods are becoming obviously more and more popular all over the country. And this is a little slide sequence put out by Lawrence Livermore Lab. This is the call for green buildings, and obviously you reduce carbon footprint, you get better air quality, but I like some of these other statistics, which are probably way out of date now. These are the estimated savings from disease, asthma, sick building syndrome, etc., people not coming to work. This is, I like to show this in classes, if they had better windows and renewable energy, all the students would be 20% better in math, read 25% better. If you take a look at the hospital example, stores would sell 40% more. If you take a look at if people are recovering in hospitals that have nice open windows, this is no doubt the coast of, this is Colorado, no doubt over here, then it turns out people recover much faster. The other thing, which I didn't actually put down on here, which had occurred to me as I was driving over, is actually our biggest resource, it should be right on the top here, is water. Maine's not going to run out of water. We have tons of water. The storms may come, but they just bring more water. We won't have as much snow, potentially, but we will have a lot of water. And so we could become an amazing resource for energy and an amazing resource for water and clean water. As I said, October 23rd, we have a conference at the University of Maine. You can look it up on our website. We show people how to use this software that allows you to see how temperatures have changed. You can look up where you live. any part of the world, see how drought is impacting. We also have this air quality indicator. We've also developed this system by which you can map vulnerabilities, things that might change, that your community is vulnerable to as a consequence of climate change. And I'll just conclude with this. In my opinion, we've entered this age of climate decision. There's no doubt about it. And if we do the right thing, it's win-win in every possible case. We have a lot of responsibility, but again, I think to deal with, but we have great opportunities. And while the fight for mitigation is not doing too well, we need to continue to make sure that we reduce greenhouse gas levels and certainly reduce toxic substances in the atmosphere. Greenhouse gases last in the atmosphere for hundreds of years in the Earth's system. But the toxic substances like cadmium and small particulates drop out in a matter of days. During 9/11, when the aircraft were shut down, it was the cleanest that the air was over the United States in decades. It happened that fast. So we need to think about the obvious reality that we need to adapt to these changes, and we need to figure out ways in a growing population and in a changing climate and shifting of air, of water and pollution, how we're going to sustain. But again, if we have good information, I think we can do a better job and make effectively lemonade out of lemons. Thank you very much. Thanks for your patience. If you're eager to leave, please go. If you would like to ask some questions, I'd be happy to answer them.
And just a reminder about the evaluations, if you could try to finish those up so that we can do the drawing after the session.
Otherwise, Suzanne doesn't continue to get money from NOAA.
No pressure.
So, any questions? Yes.
You raised the question of, well, or the fact that security is really key in this. And think about the low elevation of Bangladesh, almost none of the country being over 20 feet.
Yeah.
And if we're talking in terms of the possibility of a 13-foot rise, there will be, what, 100 million refugees from that country alone?
Absolutely. Absolutely. The migration of people related to sea level rise, drought, could be massive. And it's interesting, we tend to think of climate refugees as people coming from lesser developed countries, but there are towns in Maine, there are many towns in Maine that are developing climate adaptation plans. And there are a couple in particular that are worried about climate refugees, and they're not worried about refugees from Bangladesh, they're worried about refugees coming from more southern parts of the United States. Virginia, Florida. And why are they worried about it? I think that's clearly not, I think, because they just don't want more people around. It's because of how an area changes. So this, to me, is a great opportunity. If we understand the fact that Maine will become, despite Lyme tick disease, despite increased storms and perhaps inability to travel in an aircraft as much, we're not going to be any worse off, probably better off in a lot of places. And we need to prepare ourselves for large shipping endeavors, for potentially a lot of people coming in for jobs for offshore wind power and climate refugees, some of whom are going to be super wealthy and buy up large amounts of land. Others who will just be coming here because this is going to be a great place to live. Yes?
I came to this very room about 5 or 6 years ago to hear another lecture on climate change, and it was given by Lou McCown, who was a weatherman.
He got his PhD with us. Yep.
And he said back then that he said some scientists were predicting that if you drew a line from, I think it was Toronto, Canada, across to Scotland, equidistant down over and back up. He said that square of Earth, which we're sort of right in the middle of, was going to become one of the wettest places on the planet, and other, but basically the rest of the planet was going to become very dry. But he also said that there was a potential that section of Earth was going to go into a, possibly over a long period of time, and slowly, a mini ice age.
Yes, and he was talking about this change in ocean circulation that is related to adding fresh water to the North Atlantic. If you slow down the heat transport, and the biggest thing that we export from the United States to Europe is actually warm air. I won't say hot air, that doesn't sound good, but warm air. If you shut down how fast this overturn occurs, you actually have less heat going into places like Scandinavia. And there is the possibility that as we reduce that heat, that area will cool. I mean, we already know that with warming, the Southern Ocean is cooling because of what's related to the winds. Turns out that because of those increase of winds in the Southern Hemisphere, the coast of the western coast of South America, the lower half, is actually cooling because cold currents are speeding up. They hit the coast of South America and they're pushed up along the shore. And if you even go to the east coast of South America, where you have the Falkland current, ocean current, biologists are noting that penguins are going farther north. So there are going to be these anomalous places. I don't think there's going to be an ice age in Europe, and the next ice age is going to be a long way off. But certainly there are going to be places where there is cooling. And it's interesting that the skeptics really never picked on the fact that Antarctica is very significantly, Antarctica is cooling very much, or that there's more snow on the southern west coast of South America. The other thing that's interesting is that while the amount of sea ice in the Arctic is at its greatest minimum for the satellite era, which is the last 35 years, the Antarctic sea ice at the same time was at its maximum of the last 35 years, because as these winds revolve around Antarctica, they're actually creating a barrier that there are several ways to explain it, but one straightforward way is the sea ice is basically being kept in place. So all of these things that we never expected would happen, all these surprises, how fast the Arctic sea ice opened, the fact that it increased the winds, which almost ineffectively is protecting Antarctica for a while. Now with some of these surprises that appeared that scientists didn't actually think would happen, we're becoming smarter about looking, not just assuming the whole planet will get warm, but that there will be these anomalies generated, in fact, by this dramatic difference in temperature gradient. It all comes back to greenhouse gas warming and ozone depletion over Antarctica, but how it actually plays out is not as straightforward as just getting warmer everywhere.
So you can't really tell when you were describing those winds, when that barrier around south the Antarctic will dissipate or less?
Well, we do know that the intensification is probably unique for the last 5,000 years, based on our records. And we do believe, a growing community of scientists believe that when the Antarctic ozone hole heals, that barrier will weaken, that wind barrier speed will weaken. So the question is, when will the Antarctic ozone hole heal? And it's a gas. And the best understanding is it'll take 50 to 100 years for the Antarctic ozone hole to heal. And the Montreal Protocol, which reduced a lot of chlorofluorocarbons that destroyed that, was enacted, 20 years ago, something like that. So, now, within the next 100 years, 80 years, that barrier will definitely weaken. I think it's going to be a lot faster than that. Everything that we look at, remember when they first started talking, me too, scientists, we said that the Arctic summer sea ice would open up in 2040, and then a little while later, 2025, and then 2015, and bang, 2011 it opened up. Literally, when people were saying it would be 2015. So it's this idea that we've all been programmed, this goes back to these challenges, to think that things work in a slow, linear way. And we need to think outside the box. Doesn't mean that it'll always be right, but we need to be prepared for these much faster changes and anomalies that we've now experienced.
Well,
Yes?
yeah, everyone's concerned about climate change. Is the underlying problem really the growth of population? Why isn't anyone addressing that?
Yeah, of course. It is a very big issue. And if you look at the rise in greenhouse gases and everything else, it's directly related to population. But of course, there are all of the issues surrounding that. But it's important to keep that in mind, particularly because that means that mitigation becomes even harder. You're pushing a stone uphill with your nose. And it also means that you need that much more mitigation in order to account for that. So these are all, unfortunately, multipliers in the wrong direction. Thank you for your time. Oh, sorry, you have your drawing?
Yeah,
And if somebody has a book that would like it signed, I'd be happy to sign it. Yes?
Is your model showing that like California drought will continue or?
Yeah, I think you have to assume that that jet stream pattern could actually, and has in the past, shifted over to the western side of the country. So it is possible that the western side of the country will be, for some period of time, locked in a wetter, colder situation, which would be good for them if they were. But the tendency, because of the mountain system, is for the jet to be pushed to the east coast. I think it would be unrealistic to say that they're going to have drought every single year for the next forever. There certainly will be times when the system shifts over, but the long-term expectation, unfortunately, is. And 70% of our food, I think, comes from California. And who knows? I don't know. I think globally, 60% of the food comes from the ocean. 40% comes from the ocean.
And the Midwest, I mean, they typically use possibly.
Yes. Yep.
And the expectation, your expectation?
Drier. The expectation is in general drier for the Midwest. Warmer, pretty much in the United States, warmer everywhere, drier everywhere except for the eastern corridor over the possibly the eastern border of Ohio. Every year, no, but if you wanted to bet on what will happen majority of over the next 10 years, that's probably the case. And that's the way to plan. The neat thing about plausible scenarios are if you don't, well, let me go back to IPCC quickly. You look, IPCC is a phenomenal document, but they rate things as least likely to most likely. So you have about 4 categories. So which one would you believe? When a scientist says, I think this is least and that's most. The other way of doing this, and what they did was fantastic. They provided an amazing framework. But the other way of looking at it is, what are some plausible things? And the military plans for plausible scenarios. And you never have one, you don't even have 2 or 3, you typically have 4 plausible scenarios. So in my mind, one is linear change, another one is abrupt change. How do you simulate abrupt climate change? It turns out to be quite easy. You take what you think might happen in 2100 and you make it happen 20 years from now. And that's an abrupt change. And then you sit down with other plausible scenarios and you begin to think, okay, between now and the next 20 years, which is a good time frame to be planning towards, not 2100, if it operated linearly or if we had this dramatic change in 20 years, then how would it progress? And then look at the community, and if it's a community that's based on coastal resources, they have a certain set of vulnerabilities. If it's a farming area, other vulnerabilities. You begin to think about how their vulnerabilities will be impacted by X changes in precipitation, 3-degree fast change in temperature. And what you're forced to do is to think about basically all of the possibilities. And then one needs to decide how bad a possibility do you prepare for. But if you don't think about the full range of possibilities, you never know what to prepare for. Yes? Oh, sorry.
Given all of the evidence that you and other scientists have pulled together, why is there still seemingly traction out there amongst the doubters?
Several reasons. One is there's a tremendous surge of misinformation that came out in about 2007, 2008. Prior to 2007-8, you look at the internet, you look at global warming, and it was just, everything was in favor. All of a sudden, it all changes, and those become the headers. It's because you can manipulate the internet quite easily, if you have enough money to do it. The reason that people doubt these sorts of things, there are a whole bunch of reasons. One is based on basic beliefs, and I'm not talking about religion or anything else, just the way you're made up. Some people are more skeptical, some people just don't want to accept the fact that change can occur, or they assume everything that happened in their life worked in a certain way. Another reason is that if you can plant the smallest amount of uncertainty in people's minds, that immediately changes the situation. That's obviously the way one attacks political candidates. And in the case of, there are a lot of surveys that have been done. It's a very big field now, trying to figure out why people think what they do. And in the case of climate change, if you take a look at the surveys, the believers in climate change in this country are about 50%. If you ask people, however, how many people trust scientists, it's about 85 or 90%. And then if you ask them, how many scientists do you think believe that climate change is produced by human activity, they won't say 98% or 95%, they'll say it's split. And that's because of misinformation. So you have enough uncertainty in there, and even though they believe scientists, I heard, I won't say who it was, I heard a broadcast today from a candidate who was asked, do you believe that climate change is real? And his statement was, well, there are a lot of scientists who believe there's a problem, there are a lot of scientists who don't. That's not true. The 98%, 95% believe that this is really happening. To become a little, bore down a little bit more, one of the organizations that's been very, very effective in this misinformation is the Heartland Institute. And the Heartland Institute published a page of the New York Times with a list of thousands of scientists who presumably agreed with their viewpoint. I know I was on that list, and I'll bet you were on that list, and none of us ever signed that report. But we had said something in a paper. I said that solar variability was an important mechanism in climate change. Well, of course it is, certainly, and it's the whole idea of ozone, and it was much more important before humans were around, but they simply take that. So I contacted them and I said, take my name off there, and they said, no, you wrote a paper, we want to recognize what you did along with this. So I went to Scott Pelley, who I work with a lot at CBS 60 Minutes. I asked him some advice, and he said, okay, I'll call them up and see if they want to do a story about this, about the fact that you want your name off that thing. Obviously, my name came off. But all the other names, and everybody remembers that there were 10,000 names on that list. The Heartland Institute was interviewed by, I've forgotten his name, he's a reporter at MSNBC, and he kept boring down on the leaders of the Heartland Institute, and he said, what is it that you really, what's the real basis for your disagreement with climate change? And one guy, I forgot his name, but he was very high up, eventually said, it's really not about the climate system, it's about government control. And we just don't want more legislation. So the successes of acid rain. So that means, you can understand all of these viewpoints, but that means that climate change will not be resolved solely by legislation. It's got to be a ground up. And places like Maine, where the communities are really, really becoming very energetic about this, it's a very positive direction. Eventually, federal governments and small communities will meet and come up with the right ideas, because it's a win-win situation. It's healthier, it's cheaper, you save money on it. The reasons are endless.
The other reason is that the media feels compelled to, give this side and then the other side. So you get creations of, so people then think, well, there are two sides.
And that's why you should watch Years of Living Dangerously. I don't get any money if you watch it, but you should watch it because it's the first documentary I've ever seen in which they look at the political side, they look at small towns in very conservative areas where people don't believe this, but where they've been dramatically impacted. The bottom line is that the solutions are almost all the same thing. Some people don't want to say humans did it, but they still want to find a way, but they believe that change will occur. It's natural. It doesn't really matter what people believe. If you begin to make these changes, the net result is we become better prepared. The net result is we reduce greenhouse gases, we reduce energy, so you get the same solution. Pick one of these? Sure.
Two.
There's one. Good.
One. Okay.
There we go.
Hooray! The winners are Joan and Peter Griswold. Hooray, hooray! And Dugovic. And you can have
So, one more question, yes.
I was wondering about wind fans out there in the ocean. What about birds and
What about birds?
birds and
Oh, for the windmills. Absolutely right, and that's why I did mention that there are environmental concerns, and there are also, obviously, marine ecosystem concerns. But the cost of this system is going to be in the hundreds of billions of dollars to do it correctly. And I think that if the state of Maine, for example, were to do the same sort of thing they do when they build public buildings, every public building built in the state, 1% of the cost has to go towards artwork, to maintain the arts in the state. If in fact we put the same sort of tax on the construction of these windmills, that some percent goes into studying all of these things so that you can put it in the right place. People are developing new sensing systems for finding flocks of birds. There are ways of deterring them. There are, so that you can put systems upwind where the birds are coming from that'll force them to move in different directions. It's not going to be a perfect solution by any means, but it sure beats killing the entire ocean from acidification and everything else that goes along with it. But I agree, and this is an important thing for us to be studying. How birds and marine ecosystems will be impacted by these things. They'll be quite far offshore. Okay, thank you.
So much.